Welcome. In this e-learning module, I shall demonstrate and make you understand how to design the spring for the strip pusher. In the previous e-learning modules, we had designed the strip pusher and the shoulder bolt. To complete the strip pusher mechanism, we need to insert the spring between the shoulder bolt and the strip pusher. We should insert washers before we insert the spring between the shoulder bolt and the strip pusher. Let's create this washer, with an inner diameter of 11 mm, an outer diameter of 21 mm, and thickness 2 mm. This drawing is available for you to download below this video player. Create a new part file with the part name as spring. Create a sketch on the front YZ plane. Sketch two circles with origin 0, 0 as the center of the circle. Update the diameters of the circles to 11 mm and 21 mm. Make sure the sketch is fully constrained and exit the sketcher workbench. Create a pad of thickness 2 mm. Set the view to isometric and fit all in. Save the washer. Swap the window to the die assembly. Let's assemble the washer to die assembly. Click on the existing component command. Pick the product 1, which is the die assembly. Pick the washer from the file selection window. Use the manipulation command and drag the washer. Provide a coincidence constraint between the shoulder bolt's axis to the washer's axis. Provide a surface contact constraint between the strip pusher's front surface and the washer's back surface. Update the assembly. Let's assemble one more washer to die assembly. Click on the existing component command. Pick the product 1, which is the die assembly. Pick the washer from the file selection window. Use the manipulation command and drag the washer. Provide a coincidence constraint between the shoulder bolt's axis to the washer's axis. Provide a surface contact constraint between the washer's front surface and the shoulder bolt head's rear surface. Update the assembly. The space between the washers looks small. Let's increase the length of the shoulder bolt. Right-click on the shoulder bolt and open it in the new window. Double-click on the shoulder bolt and update the shoulder bolt's length from 40 mm to 50 mm. Set the view to isometric and fit all in. Save the shoulder bolt. Swap the window to the die assembly. Update the assembly. Measure the distance between the washers. The measured distance is 28.5 mm. This is the space available for the spring. Set the view to isometric and fit all in. Save the die assembly. Let's get started with the spring design. Spring design is a three-step process. In step 1, we shall calculate the push force. In step 2, we shall calculate the spring constant. In step 3, we shall select the spring. Let's get started with step 1, we shall calculate the push force. You see on the screen, the strip pusher mechanism used to push the strip against the rear strip guide plate. A certain amount of force is required to push the strip. Let's call this force the push force. During the strip layout design, we had designed the strip with width 71.5 mm, length 2,500 mm, and the thickness 3.15 mm. We can easily calculate the volume of a strip by multiplying its width, length, and thickness. By multiplying the volume with the density of steel, we can calculate the mass of the strip. By multiplying the mass with acceleration due to gravity, we can calculate the strip weight. The force required to push the strip can be calculated by multiplying the strip weight with the coefficient of friction. Note, I have considered the coefficient of friction as 0.7. The calculated push force is 30.8 Newton. The spring that we design should apply a minimum of 30.8 Newton force to push the strip. The spring force should be enough to push the strip. At the same time, the force should not be more. If the spring force is more, it will resist the movement of the strip. The operator will find it difficult to feed the strip. The push force calculation has some drawbacks. Practically, we are not pushing the entire strip against the rear strip guide plate. We are pushing only a portion of the strip against the rear strip guide plate. The operator shall also try and position the strip against the rear strip guide plate. Also, we have applied the coefficient of friction to the entire strip weight. But as you can see, only a portion of the strip is lying on the die plate. To compensate for the drawbacks in the calculation, I shall consider the push force as 50% of the calculated force. So, the push force for which we shall design the spring will be 15.4 newtons. Now let's calculate the spring constant in the second step of the spring design process. What you are seeing on the screen is the drawing of the strip pusher mechanism. Let's take a closer look at the strip pusher mechanism. As you can see, the space available for mounting the spring is 28.5 millimeters. Remember, we had measured the same value on the 3D design. Generally, when we mount the spring is preloaded by 5% to 10% of its length. For example, a spring of 10 mm is mounted in the space of 9 mm, so that the spring is always compressed by 1 mm. This compression is called preload. We can calculate the total length or free length of spring by dividing the space available by the preload amount. 28.5 divided by 0.9 gives us the total length or the free length of spring as 31.7 mm. Generally, springs are available in steps of 5 mm length. Hence, we can finalize the total length or the free length of spring as 30 mm. Note, with 30 mm as the total length or the free length of spring, the preload is 5%, which should be just okay. Now let's calculate the compressed length of the spring. Remember, we had designed the strip pusher 2 mm inside the strip. Practically, when the strip is inserted, the strip pusher comes back by 2 mm. This 2 mm is the stroke of the strip pusher. By subtracting stroke from the space available to mount the spring, we can calculate spring's compressed length. 28.5 minus 2, which is equal to 26.5 mm, is the compressed length of spring. Also, note, at 26.5 mm, we need the push force of 15.4 newtons. The spring constant can be calculated by dividing the push force by the total stroke. Total stroke is the difference between the total length and the compressed length of the spring. 15.4 Newton divided by 3.5 millimeters, we get the spring constant as 4.4 newtons per millimeter. Hence, we need to select a spring with spring constant 4.4 Newton per millimeter or more. Now let's calculate the maximum compressed length of spring. The maximum compressed length of spring can be calculated by subtracting the maximum stroke from the space available. Note, the maximum stroke is 3 millimeters. An additional 1 millimeter is the clearance between the strip and the front strip guide plate. While the strip is inserted, there is a possibility that the strip pushes the strip pusher by an additional 1 millimeter. 28.5 minus 3, which is equal to 25.5 millimeters, is the maximum compressed length of spring. Maximum deflection can be calculated by dividing the difference between the total length and maximum compressed length by the total length. The calculated value of the maximum deflection is 15%. Hence, we need to select spring with allowable deflection 15% or more. Now let's select the spring in the third and final step of the strip pusher's spring design. 10 mm is the diameter of the shoulder bolt's shank. Hence, the inner diameter of the spring should be more than 10 mm. We have already calculated the free length of spring as 30 mm. The spring constant is 4.4 newtons per millimeter. The maximum allowable deflection of the spring should be more than 15%. By referring to any spring catalog on a spring manufacturer website, select a spring matching these criteria. I recommend you search on the internet and choose the spring. I have selected the spring. The outer diameter of the spring is 14 mm, the wire diameter is 1.7 mm, and the maximum force of the spring is 88.3 Newton. Now let's create the 3D design of the spring. We will design the 3D as per this geometry. Create a new part file with the part name as spring. Change the workbench to wireframe and surface design. Pick on the helix command. Select height and pitch for the helix type. Enter the pitch as 2 mm. Enter the height as 28.5 mm. This is the length of the spring. Right-click on the starting point and select Create a Point. Enter the Y value as 12.3 divided 2. 12.3 is the mean diameter of the spring. Click on Preview, make sure the point is getting created, and then click on OK. Right-click on Axis, and then select the Z component. Click on Preview, make sure the helix is getting created, and then click on OK. Change the workbench to Part Design. Create a sketch on the front YZ plane. Sketch a circle, with the center of the circle on the X-axis. Apply a coincidence constraint between the center of the circle and the start point of the helix. Update the circle diameter to 1.7 mm. This is the coil diameter of the spring. Make sure the sketch is fully constrained and exit the Sketcher workbench. Create a rib with the circle as the profile and the helix as the center curve. Click on Preview, make sure the spring is getting created, and then click on OK. Create a sketch on the front YZ plane. Sketch 2 rectangles. Create a dimension for the height of the spring. Update the dimension to 28.5 mm. Apply the symmetry constraint between the rectangle's left and right edges with reference to the vertical axis. Make sure the sketch is fully constrained and exit the Sketcher workbench. Create a cut with the Pocket command with a mirrored extent. Observe the ends of the spring is cut. This is the spring with ground edges. Let's provide a formula to the spring. Click on the Formula command. The Formulas window opens. Click on the sketch created for cutting the edges of the spring. Pick the spring height dimension. Observe the dimension that is highlighted in the Formulas window. Click on Add Formula. Observe the Formula Editor window opens. Click on the helix. Select the height dimension of the helix. Observe the height dimension of the helix is highlighted in the Formula Editor window. Click on OK. Observe a formula is created, indicating the height of the spring on the Pocket command is equal to the helix height. Click on Apply, and then OK. The advantage of this formula is that if you change the helix's height, the height of the Pocket automatically updates. Set the view to isometric and fit all in. Save the spring. Swap the window to die assembly. Let's assemble the spring to die assembly. Click on the existing component command. Pick the product 1, which is the die assembly. Pick the spring from the file selection window. Use the manipulation command and drag the spring. Provide a coincidence constraint between the spring's axis to the shoulder bolt's axis. Observe there is no reference element for the axis in the spring. Swap the window to spring. Let's create a line at the center of the spring. Pick the line command. Select the point direction for line type. Right-click on point and select Create a Point. Create a point at the origin 000. Click on Preview, make sure the point is getting created, and then click on OK. Right-click on the direction and select Z component. Enter 0 as the start. Enter 20 as the end. Click on Preview, make sure the line is getting created, and then click on OK. Save the spring. Swap the window to die assembly. Provide a coincidence constraint between the spring's axis to the shoulder bolt's axis. Provide a surface contact constraint between the spring top surface and the washer's front surface. Update the assembly. Observe the spring is assembled in its position. Set the view to isometric and fit all in. Save the die assembly. With this, we have successfully designed the spring for the strip pusher mechanism. That's all in this e-learning module. Thanks.